In this video, we're going to review how to solve the linear perturbation equations for acoustic waves in the fully compressible Navier-Stokes equations using the determinant method for a constant coefficient system. The fully compressible Navier-Stokes equations for an ideal gas with no diffusion appear at the bottom of the screen. These are the order epsilon fluctuating equations where the epsilon squared nonlinear terms have already been removed. The first thing that we want to do in solving this system is to consider the constant coefficient system. A constant coefficient system is a system that we can solve using pencil and paper, whereas a non-constant coefficient system will require numerical techniques. When we talk about coefficients in the equations, what we are talking about are these terms, the multiplicative terms that appear in front of our linear waves. So our linear variables are the subscripted 1 variables, t1, u1, log rho 1, and we have some coefficient terms, grad log rho 0, t0, the gas constant r, and the ideal gas gamma. If these coefficients are constant, then we have a system that can be solved analytically by simple techniques. One constant coefficient solution to this system is if t0 is a constant and grad t0 and grad log rho 0 are both 0. We'll talk later about times when they're not 0, but this is one of the simplest systems to solve. We also have that the gas constant R is a constant and that the gamma of the gas is a constant. So R and gamma are constant. If we take a look at our equations under the assumption that grad t0 and grad log rho 0 are both 0, and that means that this term here is 0, as is this term in the continuity equation and this term in the temperature equation. This leads to a simplified set of equations for constant coefficient fluctuations, which we will rewrite next. So these are, under the assumption of constant t0 and grad t0 and grad log rho 0 are 0, these are that d by dt of log rho 1 plus the divergence of u1 is 0, that d by dt of u1 plus the gradient of r t1 plus r t naught grad log rho 1 is 0, and that d by dt, that our temperature fluctuation equation, d by dt1 plus gamma minus 1 t0 and the divergence of u is equal to 0, u1. Okay. Now, to make progress, we're going to take 1D waves, and we're going to assume a Fourier decomposition. We're going to say that u1, t1, and log rho 1 all scale like e to the I k x minus I omega t. So we're assuming a Fourier decomposition in both space and in time. Taking this Fourier decomposition allows us to turn the calculus in the system into algebra and write this down as a linear system of algebraic relationships. I'm going to write these down next. So this system, starting with our continuity equation, this is I omega log rho 1. So this comes because d by dt acting on any of our variables transforms into I omega times our variable. So we have I omega log rho 1, and we have I k times u1. This is our divergence of u quantity when written in a one-dimensional sense. In that equation, we have no dependence on temperature. And I'm going to write it in this form so the matrix version is clear in a moment. Our momentum equation has a dependence of minus I k r t 0 on log rho 1, and it has the dependence of I omega plus I omega on u1, and then the temperature dependence in the momentum equation comes in as the gradient. So let's make this actually a minus, because gradients of variables, they go as minus I k in our above decomposition. Our gradient is minus I k r t 1 equals 0. All right, our last equation, our temperature equation, it has no dependence on log rho 1. It has a minus I k gamma minus 1 T0 dependence on u1, and it has an I omega dependence on the temperature, I omega T1 from our time derivative term. I've written this here as a set of linear equations. We could also write this, of course, as a matrix I omega minus I k and 0, and then minus I k r t0 I omega minus I k, and then 0 minus I k gamma minus 1 T0 I omega. This is our matrix operating on the vector of our variables, log rho 1, u1, t1 equals 0. So this is a matrix A. This is our linear operator matrix A operating on our set of variables x, and the whole system is equal to 0. Now, when will this system have interesting solutions? We have basically two conditions on the solvability of A. One, if the determinant of A is not equal to 0, then there is only one unique solution to AX equals 0. That solution is the null solution, is x equals 0, and that is pretty boring. The only solution that exists is a solution with no waves at all and no motion, no waves. The alternative is that if the determinant of A, so our alternative, if the determinant of A is equal to 0, then there are either no solutions, or, here's where things get interesting for waves, or there are infinitely many solutions. And it turns out the second condition, the infinitely many solution branch, corresponds to linear waves. So to find the linear waves in our system, we're going to look and see if the determinant of the matrix of A is equal to 1. Now, what is the determinant of our matrix A? The determinant of our matrix A. Well, that's the determinant of the 3 by 3 matrix that I wrote up above. And we can remember how to solve for determinants. And that matrix determinant, when we write it out, given the matrix I wrote to you above, looks like this. It looks like I omega for the first term. And we calculate a 3 by 3 matrix by taking the entries. So if we go back up to our matrix here, our method for calculating the determinant of a 3 by 3 matrix, we take the entries in the top row here, and we multiply them by the subdeterminant in the other corner here. And then we do the same here for the subdeterminant of the outer columns, and then we do the same here, but here it's 0. So if we do that, paying attention to the sign conventions as we go to the middle column, then what we get is the following. We get the I omega times the subdeterminant, which is I omega quantity squared, then minus the quantity I k squared times gamma minus 1 r t 0. That's our first subdeterminant. And then our second subdeterminant, this one comes in as I times k times the parentheses minus I k r t 0 times I omega. That's the subdeterminant that it hits. So here's our system, and we can simplify this a little bit. As we gather our terms, we can see that this turns into I times omega times a quantity k squared times gamma r t 0 minus omega squared. And this is equal to 0 if we have solutions to our waves. Now, if the first part is 0, if I omega is 0, then again we have no waves, and that's boring. So that must mean that this middle part must be 0 all by itself. And what that means is that omega squared is equal to k squared times gamma r t naught. And this has infinitely many possible solutions because there are infinitely many possible omegas and k's, and they are related by this constant number here. This constant number here has the units of meters squared per second squared, and this is the adiabatic sound speed squared. Adiabatic sound speed. Squared. Now this relationship between omega and k squared is called a dispersion relationship. So omega is gamma r t naught k squared, which is also the adiabatic sound speed squared, k squared. This is the required condition for there to be solutions to our waves, and this required condition has told us something about how the frequency of the waves, omega, is related to the wavelength of the waves. And the way that the frequency and the wavelength are related is by this sound speed in this dispersion relationship. We can check our units. Omega has units of 1 over time squared. It says units of 1 over time squared. K has units of 1 over length squared for k squared. And with our sound speed squared, this is length squared per time squared, and our units work out. Next time we will learn how to use dispersion relationships to learn more about waves, once we've learned a bit more about how to solve waves using other approaches.